Hello class, welcome to our lesson today dealing with section 10.5. We're going to expand on some of the fundamental counting principle ideas and look at that when it comes to what are known as independent and dependent events. So hopefully some of those pieces that you may have been missing from the earlier part of the chapter will make a little bit more sense as we look at today's lesson and the next lesson dealing with section 10.5. Before we get into the probability aspects of today, I want to look at a few simplifying questions. So this first one, remember you have to distribute. Negative 4 times 3x would be negative 12x. Negative 4 times basically a negative 5, because you can make minus 5 into plus negative 5, becomes a plus 20. From here, it's just combine like terms. So negative 12 minus 7, those are both negatives. So you add them together and you get negative 19x. 20 plus 3 is 23. In the second one, I just chose to combine the x values together first, so plus x minus 11x. Remember, this plus x is plus 1x. If there's not a coefficient in front of the variable, remember that there's a 1 there, and that would be negative 10x. And then you just add all the other parts. So 4 plus the 9 is 13. 13 minus the 7 would be 6. And then plus negative 5 is the same as minus 5, and that would become a plus 1. Remember, you can only combine things that are like terms. So x's go with x's, y's go with y's, constants without variables go with other constants without variables. Okay, what we're going to look at here is looking at a situation where you have 3 marbles. You have 2 greens and a purple. This first one says we're going to draw a random marble from the bag, put the marble back, and draw it again. So that's what's known as called with replacement. Okay, so if whatever you draw, if you put it back, okay, that's typically called with replacement. And so what this is this is the tree diagram, more of a visual. Okay, you could have picked green, green, or purple. Now the key is you have to think of it like this is green 1 and green 2. In the end, the result is that you get a green, but there's 2 ways that you can do that. And then on the second draw, notice that there's 3 options because there's still 3 marbles in the bag because I put the marble back that I drew first. So that could be green, green, or purple. Green, green, purple, green, green, purple. I just went down the list and figured out what the final options were for the 2 draws. So for the first group, it could have been green, 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 or green, purple. And I just went down all of these tree diagrams to figure out all 9 options that are possible. And then the question is, find the probability both marbles are green. Well, one way to find that is based on the sample space that I just wrote out. Okay, these 9 options, how many are green, green, or both green? 1, 2, 3, 4 of the 9 options. That's one way to find that probability. The other option about finding probability, which is what we're going to be looking at more as we move forward in our probability unit, is to just do the fundamental counting principle idea. Find the probability the first one's green. Well, that's 2/3 because 2 of the 3 marbles are green. Times, well, since I put the marble back, it's just 2/3 again. So 2/3 times 2/3 would also be another way to get 4/9. These are independent variables. Okay, drawing of the first marble does not impact the drawing of the second marble. Okay, so these are what are known as independent variables or independent events, excuse me, and that was a with replacement situation. The second example is done without replacement. So it's drawing 2 marbles out of the bag. Now sometimes people draw both of them at the same time. You might see this with dice rolling when you roll 2 dice. If you have ever seen someone roll 1 die, then roll the other die, really they're rolling both dice, they're just choosing to do it one at a time. This is kind of the situation of this tree diagram. So the first one could have been green, green, purple, but since I drew the first one, if the first one's green, I only have green, purple left. For the last one, if I drew purple, there's no purples left, so it has to be green, green. Notice that there are 6 options now instead of 9. The last one had 9 options because it was kind of 3 times 3. This one has 6 because it's 3 times 2 because it's without replacement. There's only 2 of the 6, or 1/3, that are both green. I could find that by using the sample space here at the bottom. I could also say, well, 2 of all of the 3 marbles are green. But if the first one is green, then it's 1 out of 2 for the second group, and that becomes 1/3. The second draw is dependent on the first draw, so these are without replacement. And anytime you see without replacement, that is typically a dependent situation. So we're going to look at our own experiment. We have 3 green pawns and 2 red pawns. We're going to draw a pawn, put it back, then draw another one. If we were able to do this kind of as a group, we would collect all our data and kind of see what happens. Okay, but let's just think about this idea. Draw the 2 green pawns. So the probability I draw a green pawn is 3 out of 5 because 3 of the 5 pawns are green. Times, since I draw the pawn, I put it back, times another 3 out of 5 because for the second one to also be green. That would make it 9 out of 25 as a final answer, and that would be my probability I draw both green. This question is a independent events or with replacement. You can imagine if you already kind of thought about it, the next one's going to be a without replacement. You draw the 2 pawns together or one at a time, but you don't put it back. So there were 3 out of 5 to start with. That's the same as the last slide. But now since I took one of the green pawns off to the side, now I'm left with 2 out of 4. That simplifies down to 3/10 as my final answer, and that would be my final answer for a simplified version of drawing 2 green pawns without replacement, which means they're dependent events. Okay, so main idea, dependent versus independent is a matter of with or without replacement. When you think about real life examples of this, the key is whatever you draw, do you put it off to the side or do you put it back into the bag or back into the group? Okay, so you can think like card games, whether it's independent or dependent events. Whatever you're looking at, the key is do you put it back or not, and does it change that probability the next time around? So that's what you want to think about when you think about real life examples of dependent versus independent events. Okay, so right here, roll an icosahedron. Remember that's a D20, 20-sided die for the icosahedron, and spin a spinner. The rolling of the die doesn't affect the spinner, so those are independent. Second one, draw a tile out of the bag. Don't replace it. Draw another one. The key is don't replace it. So if you don't replace it, that means it's all of a sudden dependent as opposed to independent. And the last one, if you spin a spinner, see what number it is, then spin again. Those are independent events because the spinning of the spinner doesn't matter, and then you spin it again. Now, some people would try to claim that's dependent because it depends on how fast you spin the spinner. You always want to assume that things like this are always done in a similar fashion every time. Like if you were conducting the experiment, you would want to make sure the spinner is spun in the same amount of force every time. So you probably have some type of robot arm or something pushing it. That's what you want to think about when you think about dependent versus independent in these cases. Okay, your homework today has 2 pieces, section 10.5, numbers 3 through 8, and 27 through 30. And then I want you to write down the key ideas section for both probability of dependent events and the probability of independent events, because we're going to use that in tomorrow's lesson. And I want you to already have that written out so it's ready to go for our next lesson. Have a good day, everyone.